Good day, everybody, and welcome to iChem. We are in our discussion of acid-base chemistry, and we want to talk about this concept right here, titration. Consider the titration of 50 mils of 0.125 molar hydrochloric acid with sodium hydroxide of unknown concentration. Describe how you would do this titration. So we need to talk about titration. Titration. And what specifically is titration? Well, it is a form, they would say, a form of quantitative analysis, used to determine, and here's the important part, used to determine the concentration, the unknown concentration of a base by reacting it with an acid of known concentration. Okay? Cool. And maybe I should be more specific. This is really acid-base titration. We can have other titrations, but we're only going to focus on acid-base titration. So what are we going to do? We have an unknown concentration of a base, and we're going to react it with an acid, and we know the concentration of the acid. So by knowing the concentration of the acid and the volume, we can figure out what the concentration of the base is. Now, it doesn't have to be that way. It can also be what? It can be a quantitative analysis used to determine the unknown concentration of an acid by reacting it with a base of known concentration. So I could either go acid to base or base to acid. Good. So that's what titration is. Now, what is my process for titration? What are we going to do? Well, let's talk just about an unknown. Let's say we have an unknown base concentration, and we have a known acid concentration. Okay, so here's what we're going to usually do. We're going to take, we're going to first determine the concentration of the acid. And how we might do that is we might take a solid acid and dissolve it. And we want to get as many sig figs out of this as we can, right? And so then we're going to take, say, a volume of this acid and put in a flask, an Erlenmeyer flask. And then we want to do something that we say we want to add an indicator. Well, what's an indicator? Well, an indicator is, let's come over here. What's an indicator? Yoink. An indicator is something, a substance, which changes color at the equivalence point, or close to the equivalence point of a titration. Oops, new word there. Hey, how about a titration of a titration? Got it. And then that brings us to a new word, equivalence point. What's the equivalence point? Equivalence point. What's the equivalence point? This is the point. I'll give you two definitions here. This is the point of stoichiometric equivalence. Stoichiometric. I can spell eventually. Equivalence. What does that mean? That means I have perfect stoichiometry. No excess, no limiting, right? In a reaction. Or for us, more specifically, I find this to be a little more helpful. This is the point in a titration at which moles of my hydroxide equal moles of my H plus or hydronium. This is what I find the most valuable definition of the equivalence point. Got it? Okay, so back to here. So I add an indicator. What does the indicator do? It changes color when moles of hydroxide equal moles of hydronium. Good. 4. Then what I want to do is we usually put my base in a burette. Now you want to treat the burette properly, but we'll talk about that when the lab comes. And record initial volume, and then add base to acid until indicator changes color. Indicator change. And then what are we going to do there at 6? Record final volume. And then we're going to have to come down here to 7. 7, determine volume of base added. And then 8, you can determine concentration of hydroxide. And from there, you can get concentration of your base. Okay? Now, how do we do that? Let's talk about 8. What do we know? I know my liters of acid, right? And I know my molarity of acid. So if I take liters of acid times molarity of acid, that'll give me my moles of acid, moles of H plus. At the equivalence point, what do we know? Well, moles of H plus equals moles of OH minus, right? We also know the volume. We know the volume of base, yikes, volume of base at the EQ point, right? Because we measure that. How do I get that? Volume of base is equal to initial reading. Let's see. No, it's going to be backwards. Final reading on your burette minus your initial reading on the burette. That'll give me my volume of base. So then I can get concentration of base. I guess I said this backwards. I can get I can get concentration of, yes, I can get concentration. No, I can't get concentration of base yet. I have to go here. Sorry. I have moles of hydroxide, and then I can get moles of base using my stoichiometry. For instance, if it's NaOH, then it's 1:1, but if it's BaOH2, then I have 1 mole of Ba for every barium hydroxide for every 2 moles of hydroxide. So I get my moles of base, and then finally, what can I do? I can get concentration of my base. How? By taking moles of base divided by my liters of base added. Got it? Right here's the liters of my base at the equivalence point. That's how we do this. It's a piece of cake. Let's run through one. Oh, let me show you the equipment first. Okay, this is typical titration. Here is a burette, right? That's what I mean. That's a burette. And here is a flask, or in this case, they have a beaker. I usually use Erlenmeyer flask. Sometimes you have a pH meter. If you have a pH meter, you don't need an indicator, but we don't always use those. And so sometimes you'll just add an indicator, and you slowly, that's called a stopcock. You take your initial reading here. You start adding dropwise to your acid until it changes color, and then you read the final reading, and that's how you get your amount of base added. Whew. Okay. All right, so describe how you would do this. What am I going to do? I'm going to, number one, I'm going to take my, or put the 50 mils of 0.125 molar HCl in a flask. Two, I'm going to add an indicator, and the indicator that is most often used with strong acid, strong base titration is phenolphthalein. So I'm going to add some phenolphthalein. Phenolphthalein turns its clear and acidic and becomes pink when it becomes basic. So it changes from clear to pink at my equivalence point. 3, I'm going to fill burette with NaOH. And then 4, add NaOH until equivalence point is reached. So that's how I'm going to do this titration. It says if the solution turns pink, that means I've gone from, it's switched from acidic to basic, acidic to basic. After 75.4 milliliters of NaOH has been added, what is the concentration? Okay, so first thing we're going to do is let's get moles of my hydronium, or moles of H+. And how am I going to get that? Well, for a strong acid, that's a strong acid, concentration of my hydronium equals concentration of my strong acid. So I know I have 0.125 molar hydronium. And what volume of that was added, of acid? 50 mils. So I'm going to have 0.050 liters. And what do I get out of that? Let's get out the handy dandy TI. 0.0125 times 0.05, and it looks to me like I get 0.000, that's a 0.000625 moles of my acid H+ or hydronium, right? Cool. And we know what? At my equivalence point, this equals my moles of hydroxide. So moles hydroxide equal to 0.000625. Let's make sure I did that right. 0.125 times 0.05. Oops, too many zeros. I did make a mistake. I thought that, look, let's get rid of a zero there. Hey, I've got the magic of erasers, so why don't I use it? 0.00625. That makes more sense. 0.00625 moles of OH minus, right? Good. Cool. Now, how many moles of NaOH do I have? Well, it's a 1-to-1 ratio, so I have 0.00625 moles of OH minus times 1 mole of NaOH per 1 mole of OH minus. I know this seems a little redundant, but I just want you to see how this really works, right? So now I have moles of NaOH. Cool? Great. Now, what's my volume? Well, my volume of NaOH is equal to what? Well, it says 75.4 milliliters were added, so that means my volume is 0.0754 liters. Good. So then, how do I get the concentration of NaOH? Take my moles of NaOH, 0.00625 moles of NaOH divided by the volume of NaOH, 0.0754 liters. Zoink! Divided by 0.0754, and it looks to me like I have 0.8 0.0829 molar NaOH. Got it? It's a piece of cake. Cool. Let's make sure I did this right real carefully. Yep, when I check my numbers, that's exactly the correct answer. Good. You guys try this one. Bring me back when you're ready. Well, what do I have? I have 20 mils of 0.275 HCl. So how many moles of H plus do I have? And remember, H plus and hydronium we use interchangeably. We could have just done that. And that's equal to what? 0.020 liters times 0.275 molar. And so what do I get? 0.02 times 0.275. I get 0.0055, 3 sig figs, sorry, I need to have 3 sig figs here, moles of hydronium. And then at my EQ point, then my moles of hydroxide equal my moles of hydronium, which is 0.0050 moles of hydroxide. I am using what? Sodium hydroxide, so that means it's a 1-to-1 ratio between NaOH and hydroxide, so that means moles of sodium hydroxide equal moles of my hydroxide, 0.0050 moles of hydroxide. Cool. And then what? Takes 17.8 milliliters to reach my equivalence point. So then my concentration of that should be NaOH, right? My concentration of NaOH equals my moles of NaOH, 0.0050 moles. I dropped a 5, didn't I? Sorry, right here. 550, 550, 550. You guys got that? Sorry. 0.00550, 0.00550 moles divided by volume, 0.0178 liters, divided by 0.0178 liters. It looks like we have 0.309 molar sodium hydroxide. Cool. Piece of cake, right? Great. Let's consider this titration. The titration of 125 mils of 0.886 molar sodium hydrochloric acid with barium hydroxide. If 79.6 milliliters of barium hydroxide are required to reach the equivalence point, what is the concentration? Okay, we know how to do this. We want to find our moles of hydronium, and that is equal to 0.125 liters. Remember, to go from liters, you just move our decimal point 3 places to the left if you're given milliliters, right? Times 0.886 molar. And what do I get out of this? I have 0.125 times 0.886 equals zoink, 0.11075, 3 sig figs, so these guys are not significant, moles of hydronium. At my equivalence point, at my EQ point, what do I know? Well, then moles of hydroxide equals moles of my hydronium, which equals 0.11075 moles of hydroxide. Good. And so how many moles of barium hydroxide do I have? Well, we have to be careful here. Why? Because I have that 2 there. So I have 0.11075 moles of hydroxide. Using our mole ratio, what do we have? 1 mole of barium hydroxide per 2 moles of hydroxide. You all see how I got that, right? There are 2 moles of hydroxide for every 1 mole of barium hydroxide. So I have to divide this by 2. And I have 0.05537 moles to barium hydroxide. Good. So what's my concentration? The concentration of barium hydroxide is equal to 0.05537 moles divided by what volume was added, 0.796, 0.0796. That's what we did that right. 0.0796 liters divided by 0.0796. Ooh, magic. And I get 0.696 molar barium hydroxide. Piece of cake. This stuff is easy for you guys because you're champs. You're chemistry champs. Okay, work this one out to make sure you understand what you're doing. Oh, no, this is a new thing. I have to help you with this, I think. Cool. Okay, here we go. Let's go back. This is a titration of 30 mils. And we want to know how many milliliters are necessary to reach the equivalence point. Okay, so we need to figure out the milliliters to figure needed to reach the equivalence point. Well, that's easy. Once again, what do we know about the equivalence point? Moles of hydroxide equal moles of my hydronium. So what do we want to figure out? We want to figure out moles of hydroxide, and then from that figure out moles of hydronium, and from that we'll get milliliters of hydronium or liters of hydronium. Got it? Okay, how many moles of hydroxide do I have? 0.00125 molar times what? 0.00275. Nope, wrong. Got to read the problem correctly. Times 0.00125 molar, right? What am I talking about? I'm having real problems this morning, aren't I? I need to add my volume, 0.0300 liters, there we go, of sodium hydroxide. Sorry about that, folks. 0.00125 times 0.03 equals 3.75 times 10 to the minus 1, 2, 3, 4, 5 times 10 to the minus 5 moles of sodium hydroxide, which is equal, since it's a 1-to-1 ratio, that is equal to the moles of hydroxide. So we know that moles of hydronium equal moles of hydroxide at my equivalence point, which is equal 3.75 times 10 to the minus 5th moles now of hydronium. And then, so how many, since it's a 1-to-1 ratio between HCl and hydronium, right? When I put water in there. So that also equals then 3.75 times 10 to the minus 5th moles of HCl. Good. And I want to get liters. Remember, molarity equals moles of my solute per liter of solution. So that would mean liters equal moles per molarity. So my liters of HCl equal 3.75 times 10 to the minus 5th moles divided by, what's my molarity? Zoink, 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 zoink. 0.00275. 0.00275. Good. And what do I get? Divided by 0.00275. Woohoo! I get 0.0136 liters, which is equal to 13.6 milliliters. Got it? Does that look reasonable? Yeah, that looks reasonable. Cool. You guys do the last one, and we're done with acids and bases. Once again, we want to figure out how much, what volume, how many milliliters of HCl are necessary to reach the equivalence point. So first we want to get moles of hydroxide. Since it's a 1-to-1 ratio, it means I can take 0.125 liters times 0.425 molar, and really this starts off, sorry, moles of NaOH. I better do this step by step properly, right? Don't want to cut corners. 0.125 times 0.425, and what do I get? I get 0.05312 moles of NaOH, but it's a 1-to-1 ratio, so moles of hydroxide equal my moles of NaOH, which is equal to 0.05312 moles of hydroxide at the equivalence point. Then moles of my hydronium equal moles of my hydroxide, which equals what? 0.05312 moles of my hydronium, which also then, since it's a 1-to-1 ratio, so moles of my hydrochloric acid equals 0.05312 moles HCl. Wow, that's a little redundant. Yes, but I wanted to show you all the steps. So my liters of HCl equal my moles, 0.05312 moles of HCl over my volume, over my molarity. What was my molarity? 0.167. 0.167. And what do I get? 0.1, oops, 0.05312 divided by 0.167, and I get 0.318, which is equal to 318 milliliters. Let's see if that makes some sense. Okay, yes, I'd say that makes sense. Good. I hope you got this answer. If so, then I'm right and you're right and we're all right and the world is right. Good. That will do it for today. See you next time. Bye-bye.